In this video, you are going to learn about bipolar junction transistors. So when you say a bipolar junction transistor, it is known as a three-terminal solid-state semiconductor device that is commonly used as an amplifier or a switch. So that's what a transistor is. So transistors have three main parts, okay, which are the emitter, and then the collector. So those are the three main parts of a transistor. And a transistor is formed by joining two diodes back to back. Okay, so a transistor is formed by joining two diodes back to back. That's what I have here. You can see that I have two diodes here that are joined to each other back to back. So at this side, this is the negative side, and then this is the positive side. So in this case, you join the negative side, and then looking at this side, so this is the negative side, this is the negative side, and then this is the positive side. You join the positive side. So this is known as the PNP transistor, and then this is also known as what, the NPN transistor. So that's what a transistor is. So now you go ahead and then look at the modes of operation of the transistors. Okay, so transistors have three modes of operation. Okay, the first one is the active mode, the second is the saturation mode, and then the third is the cutoff mode of operation. So when you consider the active mode of operation, the emitter and the base junction is forward biased, and then the collector and the base junction is reverse biased, and this is used for amplification. And then when you consider the saturation mode of operation, the emitter and the base junction is forward biased, and then the collector and the base junction is also forward biased, and this is also used for switching. And then for the cutoff mode of operation, the emitter and the base junction is reverse biased, the collector and the base junction is also reverse biased, and it is used for switching. Okay, so these are all modes of operation of bipolar junction transistors. But in these videos, we will look at the saturation mode of operation. Okay, our main focus will be on the saturation mode of operation. Okay, so now let's look at how the diode is operated in the saturation mode. So in the saturation mode, you first look at the NPN transistor and then look at how it is operated in the saturation mode. Okay, so for this case, we learned earlier on that in the saturation mode, the emitter and then the base side is forward bias. That's the emitter and then the base junction. Okay, is forward bias. So looking at this side is forward biased, and then the collector and the base side must also be forward biased. So this side is also forward biased. This is because this is an NPN transistor, and then you see that this is the negative type, this is the N type material, and then it is connected to the negative terminal. And then this side is the N type material, and it is also connected to the negative terminal. So this side is forward bias, this side is also forward bias. So therefore you see that the emitter and the base junction is forward biased, and then the collector and the base junction is also forward biased. Okay, so let's look at this. So you see that the transistor has two depletion zones. Okay, so when you take this side, we have the N type, the P type, and then the N type material here. So at the end, we have one depletion zone here, and then we have another depletion zone here. Okay, so let's look at this. I've drawn this in a simplified way here. Okay, so you see that from this side, I have the emitter and then the base here. Okay, which is the N and the P type. So I've taken just this side. I've taken one side of this transistor here. Okay, so in this side we have the N type and then the P type material. So you see that the N type here, we have the electrons here as the majority charge carriers, and then we have the holes here as the majority charge carriers. But this is just a diode here, and then we have a depletion layer here. So here the holes that are closer to the electrons will be attracted, and then the electrons that are closer to the holes will also be attracted. So we have some small electrons here and then we have some small holes here. So this will form what? A depletion zone at this side. Okay, so there will be a depletion zone here. Okay, and this diode is forward biased. Okay, so therefore electrons will flow freely across this diode. Okay, electrons will flow freely across this diode. So let's look at this one also here. So you see that what the n-type material is connected to the negative and then the p side is also connected to the positive. So you see that what it is forward biased. So due to this arrangement, we have some depletion zone here. You have a depletion zone here. Okay, you have a depletion zone here. The electrons that are closer to the p-type will be attracted to the p-type material, and the holes that are closer to the n-type also be attracted to the n-type material. So then you have what? A depletion zone here. But since it is forward biased, this this zone will be easily broken. Okay, so the electrons will therefore flow easily across the diode. Okay, so since both of them are forward biased, and then current will flow easily across this transistor here from the collector side to the emitter. So in this case, the transistor will acting as a switch. Okay, it will not provide any resistance to the flow of current. Okay, so what we have here is the same thing that I have at the top here. I just separated the two diodes. Okay, the transistor is just like two diodes that have been joined back to back. So we have the N and then the P, and we have the P and then the N. So then you have what? The NPN transistor. Okay, so one thing you should know is that in the transistor, the emitter is heavily doped. Okay, the emitter is heavily doped, and then the base is slightly doped. The base is slightly doped, and then the collector is moderately doped. Is moderately doped. Okay, and also one thing you should take note of is that in the NPN transistor, in the NPN transistor, currents flow from the collector to the emitter. So in this case, you see that what the current is flowing from the collector to the emitter here. Okay, so for this to be easy, let me name the collector current IE, and then the emitter current, sorry, let me name the collector current IC. Supposed to be IC rather, and then here should be IE, that's the emitter current, and then current at the base should be IB. Okay, alright, so in NPN transistors, currents flow from the collector to the emitter here. Okay, so let's look at this. So always the collector current IC moves towards the transistor, moves to the transistor. Okay, and then the emitter current, which is IE, moves away from the transistor, moves away, and then the base current, which is IB, moves towards the base, moves towards the base. Okay, so let's look at this here. So we said that the collector current moves towards the transistor. So you see this direction here. You see that it is moving towards the transistor, and then the emitter current moves away from the transistor. So you see that the emitter current is moving away, and then the base current moves towards the base. So you see the direction here. It is moving towards the base. So that's what it means. Now let's look at some few things here. So looking at this, you see that we have the voltage at the emitter side and the voltage at at the base side. Okay, the voltage at the base side, but you see the base is connected to the positive terminal and then the emitter is connected to the negative terminal. So that's to say that there will be a flow of current from the base to the emitter. So current flows from the region of higher concentration to the region of lower concentration. So in that case, you see that what the voltage at the base is greater than what the voltage at the emitter. Okay, so since the base side is positive and then the emitter side is negative, the voltage at the base side will be greater than the voltage at the emitter side. Same here, the base is connected to the positive side and then the collector is connected to the negative side. So the voltage at the base side will be greater than the voltage at the collector side. Okay, so now that you know this, let's look at the formula for the current in the transistor. Okay, let's look at the formula for the current in the transistor. Okay, so let's look at what is happening here. So let's apply the Ohm's law here. Okay, so you see that what we have something like this. I'm going to draw this here. So you have one current moving towards this direction, another moving towards this direction, and then one moving away. So I'll name this the IC, which is the current in the collector. Current in the collector, and this name the IB, current in the base, and then IE, current in the emitter. So you know that what current moving towards the node equals the current moving away from the node. So in this case, you see that what the IC and the IB is moving towards the node, and then IE is moving away from the node. So therefore, we see that what IE equals the sum of what IB and IC. So therefore, IE will give us what IB plus what IC. Okay, so this is the relation between the emitter current, the base current, and then the collector current. So now that we know the relation between the emitter current, base current, and then the collector current, let's look at the relation between the voltages also. Okay, so for the voltage, I'm going to draw a simplified circuit for what we have here. So let's look at that one. So I'm going to redraw my circuit this way, something like this. Okay, so I'm going to name this side the emitter. This will be the base, and then this will be the collector. Okay, but I see that the emitter and the base looks the same here, but there should be differences between them. Okay, so I'm going to indicate that difference here. So when you look at this circuit, you see that the emitter current is moving away from the transistor. So I'm going to indicate that one here this way to tell us that this is an NPN transistor. Okay, so the next thing we do is that we are going to indicate the directional flow of the current in each of the paths. So from the base to the that's from the for the base current, you see that it is moving towards the base here. So that's going to be in this direction. And then for the collector current, it's also moving towards the transistor. So this is the direction here. So it will also be in this direction. And then for the emitter current, it is moving away from the transistor, which is this direction here. So that will also be this way. Okay, so from here, the next thing you are going to do is to write down the polarities, okay, for each side. So looking at this between the base and then the emitter, at this side between the base and the emitter, I see that the emitter is connected to the negative and the base is connected to the positive. So you are going to do same here. So the emitter is to the negative and then the base is to the positive. And then between the base and the base is connected to the positive, and then the emitter and the collector is connected to the negative. So the base is positive and then the collector is negative here. Okay, so looking at this top side there, you know the current will the electrons will flow from the from the collector to the emitter here. So that means that the collector side will be a region of higher concentration to the a region of what lower concentration. So the collector side will be positive and then the emitter side will be negative, telling us that what electrons are flowing from the collector side to the emitter. So now let's go ahead. So now we are going to look at the relation between the voltages. Okay, so I'm going to name this side the voltage between the base and then the emitter. Okay, so let's name this VBE, and then let's name this side the voltage between the collector and then the base. So let's name this VBC, and then this side will be the voltage between the emitter and then the collector. So let me name that one VCE. This is VCE. Okay. Now let's kind of write down the three equations that you have. So the first one will be for VBE. So for VBE, that'll be the voltage from the base to the emitter. And the base is connected to the positive side and then the emitter is connected to the negative side. So it will be VB minus what? VE. And then voltage from the base to the collector, that's VBC. For VBC also, the base is connected to the positive side and then the collector to the negative side. So that will be VB minus VC. And then for VCE also, the collector is connected to the positive side and then the emitter to the negative side. So you have what? VC minus what? VE. Okay. So the collector side is connected to the positive and then the emitter side to the what? To the negative. Okay, so now let's look at what you have here. Okay, so looking at this, you see that we have three equations here. This should be the first one, the second, and then the third equation. Okay, so you see that what VBE equals what VB minus what VE, and then you have this equation also here. You have the third equation here. So what you are going to do is that you have VC here, and then you have VE, and you have VE in this equation, and then you have VC in this equation. So what you are going to do is that you are going to do some substitution here. So now first of all, let's look at the first equation, which is VBE equals VB minus what VE. So we are going to make VE the subject here, so I can come and substitute it here. So what I'll do is that I'll take VE to this side and then I'll take VBE to this side. So let's look at that. Okay, so then I'll have what VE to be equal to VB minus what VBE. This is what I have, and then let's focus on the second equation also, which says that VBC equals VB minus what VC. So in this case, you want to make VC the subject. So I take VC to this side and take VBC to this side. So let's look at that. So this will give me VC to be equal to VB minus what VBC. This is what I'll get at the end. So when you have this, you can come and substitute into this third equation here. So let's look at that. So VCE will be equal to VC. We now know that VC equals what VB minus what VBC. So let's put it here. That's VB minus VBC, and then minus VE. And then we know that VB is now VB. VE is now VB minus what VBE. That's our VE now. So now let's simplify this. So then you have what VCE to be equal to, let's open the brackets, so that VBE minus VBC minus VB plus VBE. This is what you have now. Okay, so now let's continue. So then I have my VCE. I have my VCE to be equal to, let's like terms here. So you have VB minus VB and then minus VBC plus VBE. So you see these two can cancel out. So at the end you have VCE will be equal to minus VBC plus VBE. So this is the simplified form of the third equation. So this will be the relation between the voltages in the transistor. Now let's look at the saturation mode of operation of the bipolar junction transistor. In this case, you are considering the PNP transistor here. Okay, so we are looking at the saturation mode of operation. Okay, saturation mode of operation. So looking at this here, okay, for the saturation mode of operation, we said what the emitter and then the base side should be forward biased, and then the collector and then the base side should also be what should be forward biased. Okay, so the same thing that I have here. So looking at this, you see that for this is a PNP transistor here, and we have the p-type material here, and then that's connected to the positive terminal, and then you have the p-type material which is also connected to this positive terminal here. Okay, and then the n side is to the negative terminal side here. So you see that both of them are what, forward biased. Okay, so let's look at this in a very simplified view here. Okay, so at this point you see that I've withdrawn this diode equivalent circuit here. Okay, this is the transistor equivalent circuit here. You see that what I have withdrawn it here. So this transistor is actually made up of two diodes. So in this case, I've separated the diodes here. So here you see that what we have one diode here, we have another diode here. Okay, so what is actually happening here is that all the diodes are forward biased, right? You can see. So you see that you are connected the positive to the positive, and then the negative side to the negative side. Same here, the negative side to the negative side, and then the positive side to the what, to the positive side. So you see that what all the diodes are what, are forward biased. So when the diodes are forward biased, current flows through it, current will flow through it easily. Okay, so in this case, this is a PNP transistor where the majority charge carriers are out holes. So in this case, holes will flow across each of these two diodes easily, and since the holes are flowing through these diodes easy, that means there will be easy flow of what, current. So at the end, current will flow through the transistor easily from the emitter to the collector. That's for the PNP transistor. So in this case, you see that what the transistor is acting as a switch. Okay, this is because there is no blockage of the flow of what, current. Okay, so now let's look at the following here. So in the PNP transistor, you should consider the following. So in the PNP transistor, always the emitter current. Okay, let me first name that one first. So let's name this the emitter current, the collector current, and then the base current. Okay, so in the PNP transistor, always the emitter current, which is named IE, always moves towards the transistor. Okay, it moves towards the transistor, and then the collector current moves away. It moves away from the transistor, and then the base current, which is named IB, also moves away from the base. Okay, so this is what you have now. So let's look at each of these conditions here. So we said what, in the PNP transistor, the emitter current moves towards the transistor. So here is it here. You see that the emitter current is moving towards the transistor here, and then the collector current is moving away from the transistor. So you can see that one also here, and then the base current is moving away from the base. So you can see that one also here. And also, one thing you should know about transistors is that the emitter side is heavily doped. The emitter side is heavily doped, and then the collector side is moderately doped, and then the base side is lightly doped. Okay, so you should consider these factors here. Okay, so that's what is really happening here. So you see that at the emitter side here, there are a lot of holes here as compared to this side here. Okay, we have a lot of holes here at the emitter side as compared to the collector side. Okay, and then in the n-type material, you see that what, there are only few electrons here, so it is to tell us that what, it is what, lightly doped. Okay, so now that we know this, let's look at the equation for the equation that relates the current in the transistor. Okay, so let's look at that equation here. Okay, so you have the current in the emitter to be IE, and then the current in the collector to be IC, and then the current in the base to be what, IB. Okay, so looking at this circuit, let me do a simplified one that shows the direction of the current here. Okay, so with this, you see that you have something like this here. You have one current moving towards the direction, one moving away, and then the other also moving away. Okay, so looking at this, we can name this the IE. You can name this the IE. You can name this I, which is the current in the emitter, and then we can name this IC, which is the current in the collector, and then we can name this IB. Okay. You know that from Kirchhoff's current law, we know that the current moving towards the junction equals or the current moving away from the what, from the junction. So in this case, you see that the emitter current is moving towards this junction here, but the base current and then the collector current are moving away. So therefore, we can see that what the emitter current equals the sum of the base current and then the collector current. So then we have what I equals what IB plus what IC. Okay, so now this is the relation between the emitter current, the base current, and then the collector current. So now let's look at the relation between the voltages also. Let's continue here. So looking at this side, okay, looking at this side here, you see you have the positive side connected to the emitter. Okay, this is the emitter, this is the base, this is the base, this is the emitter. So you see that what you have the positive side connected to the emitter and then the negative side connected to the base. And you know, if this positive side means that the voltage or current is flowing from the positive side to the negative side, so therefore the voltage here will be greater than the voltage here. So this the voltage let's name this as the voltage in the emitter, and then let's name this as the voltage in the base. So in this case, you see that what the voltage in the emitter is greater than the voltage in the what in the base, because the voltage in the emitter is the emitter is connected to the positive side and then the base is connected to the negative side. So therefore the voltage in the base will be lesser than the voltage in the emitter. Okay, so same here, you see that the voltage in the emitter, okay, this side should be collector. You see that the voltage in the collector will be much more bigger than the voltage in the what in the base. Okay, so you see that what the voltage in the collector should be greater than the voltage in the what in the base. So this is what you have now. Okay, so for us to finish the relation between the voltages, I'm going to draw a simplified circuit for this transistor equivalent circuit that I have here. So let's look at that. Okay, so we have something like this here. Okay. Okay, so I'm going to name this side the emitter, the collector, and then this side will be the base. This side will be the base. But I see that where the emitter and the collector looks familiar, so we will have to separate them. So I'm going to separate them here. So we are going to separate them by using the directional flow of the emitter current. So you see in this circuit, the emitter current is moving in this direction here. Okay, it's moving in this direction. So you are going to indicate that here on the emitter arm. So this will be the direction of flow here. So this is the direction of the emitter current. This is what we have here. So now let's come and indicate the direction of flow of all the current. So you know that the emitter current is moving toward the transistor. So you have it here. And then the collector current is also moving away. So we have it in this direction. And then the base current is also moving away from the base. So that will be in this direction. Okay, the same thing that I have here. So you see this direction, I have this one here. I have this one also to be this side, and then this one also to be at this side here. Now let's write down the polarities. Okay, so let's look at between the base and then the emitter here. So you see that the emitter is connected to the positive side and then the base is connected to the negative side. So here will be positive and this side will be negative. And then looking at this side, to the base is connected to the negative side and then the collector is connected to the positive. So the base side is negative and the collector side is what? Positive. And then you know the holes are flowing from the emitter to the collector. So that tells us that what the emitter side will be of higher concentration, and then the collector side will be of lower concentration. So here will be positive, here will be what? Negative. Okay, so now that we have this, it will be easy for us to write the voltage equations here. So this have to be the voltage between the emitter and the base. Okay, this will be VAB, and then this had to be the voltage between the collector and then the base. So this will be VCB. And then this one will be the voltage between the emitter and the collector. So this will be VEC. Okay, so this is what you have now. So now that you have this, let's kind of write the equations here. Okay, so we are going to have three equations here. So first one is the VEB. So for VEB, that's voltage from the emitter to the base. I know it is moving from the positive side to the negative side. So that will be equal to voltage at the emitter side minus what? Voltage at the what? At the base side. And then we have the VCB. The VCB to from the positive side to the negative side. So that what? VC minus what? VB. And then VCE, which is VEC, which is the voltage between the emitter and then the collector. So that will be VEC. So this should be equal to from the positive side to the negative side. So that will be what? VE minus what? VC. So these are the three equations that we have. So this is 1, this is 2, and then this is what? 3. Okay, so now that we have this, let's look at how we are going to simplify this. So let's simplify the last one that we have here, okay, by doing some substitution here. Okay, so now let's go ahead. So let's look at what is going to happen here. So first of all, I'm going to take the first equation, which is what? VAB. VAB. Okay, you know VEB equals what? VA minus what? VB here. But in this last equation, we have VE here. So let's make VE the subject. So we have what? Let's take this to this side. This to this side. So then we have VEB plus VB to be equal to what? VE. But I'm going to rewrite this the other way. So then we have what? VE to be equal to what? VEB. That's VEB plus what? VB. Okay, it's the same thing. Okay, so now let's focus on the second equation also, which is VCB equals what? VC minus what? VB. Okay, so with this one too, we have VC here, so let's make VC the subject. So that will give me VCB plus what? VB will be equal to what? VC. So let me write it in the other way. So then I have what? VC to be equal to VCB plus what? VB. Okay, so now that we have VC and then VE, let's come and substitute into this equation here. So then I have what? VEC to be equal to VE, but I know VE is now VB plus what? VEB plus what? VB. So that will be VEE plus VB. Okay, minus VC, which is now VCB plus what? VB, which is now VCB plus what? VB. Okay, so this is what I have now. So from here, let's open the brackets here. So then I have VEB plus VB minus VCB minus what? VB. Okay, so let's group like terms here. Okay, so we have what? VEB minus what? VCB, and then plus VB minus what? VB. Okay, so and then I'll have VEB minus what? VCB. So therefore we see that what? VEC equals what? VEB minus what? VCB. Okay, so this is how to simplify the third equation that we have here. So this is how the transistor works when it is in saturation mode for the PNP transistor. So now let's go ahead and then look at the NPN transistor also.